This is the second problem set of doing the basic derivatives, and again we'll take the effort of trying to set them equal to the derivatives to zero to find, is there places where we have where the tangent line slope is zero, which means it's level right there, so we have a min or a max. And so we'll start with this one. This is no product or quotient rule, but it is a chain rule. So we have a derivative of the whole times the derivative of the inside. So y prime is going to equal to e x to the third minus 3x, right? E to the x when you take the derivative. Now we're going to take the derivative of the inside, and the derivative of x to the third minus 3x is 3x squared minus 3. All right, so I'm going to rewrite it so it looks a little cleaner. 3x squared minus 3 times e x to the third minus 3x. All I did was put that out front. Now, if we set this equal to 0, again, with e, this cannot equal 0. If we had an ln can equal 0, ln of 1, but e cannot equal 0. It's never going to touch 0. It will go infinitely close to 0 as an asymptote, a horizontal asymptote of 0 out in the negative direction. But it will never touch 0, okay? And so all we can evaluate here is this is non-zero. That means our only chance is that that might be 0. So 3x squared minus 3 equals to 0, which means 3x squared equals 3. Add 3 to both sides. Divide by 3. This gives us x squared equals 1, which means that x equals plus or minus 1. X equals plus or minus 1. What this tells us is that we've got this oscillation, again, of this e to the x around the origin or near the origin, where this thing has some oscillation and probably looks, again, much like the last one. Because as I mentioned, this is going to go out to infinity this way. So at minus 1, this thing probably comes up like this, and then it starts back down, and at 1, it gets there, and then it launches off this direction. So we have these derivative values at minus 1 and 1, where the slope of that derivative is equal to 0. And in the end, what this tells us is we have a localized max or min at those spots. And in this case, I think, just based on what I think this will do, it's hard to know, but it may look something like that. So there's that one. This one, so here on this one, we have y prime, and now we have the product rule, and we have, well, we don't have a chain rule, we have product rule. So this is the derivative of the first, 3x squared times ln x, plus the first times the derivative of the second, and the derivative of ln x is just 1 over x. And this is simplified pretty well. 3x squared ln x plus, we have x to the third divided by x, that's just x squared. And so, whoops, ln x. So we want to set this equal to 0. We're going to factor, get an x squared out. That gives us 3 ln x plus 1 is equal to 0. So that means that x equals 0, this is equal to 0. But we also have this. This is an interesting thing. ln of x plus 1 equals 0. So 3 ln of x equals minus 1. And now we immediately have a problem, because we'll have to find where that's the case. Now, we can divide both sides by 3. So it's ln of x equals minus 1/3. So now, if we take the e to both sides, we can find e to the minus 1/3, and on that, it's a calculator value. Or you could just leave it like that. To be real honest, I'd prefer you leave it like that. So to me, our two answers are 0 and e to the minus 1/3. Because e ln x is x. So that's x equals e to the minus 1/3. And that would be a fine solution. I don't know that I would write more than that. So here are the two places where these are 0. Again, I'm not sure. This graph, this thing is going to go way off negative and go positive real strong. and then there's some places here. Now you would have to check to see, does the original value exist in the graph at this point? If you try to put these in, I think you're going to find that e to the minus 1/3 does produce a value, but 0 does not, because ln of 0 does not exist. So that one's not going to work because the ln of 0 does not exist. So anyway, that's how these two problems are done. I'm mainly looking for, can you do the derivative? I'm pushing this extra step because this is where we're headed, which is then, so that's not part of the solution because ln of 0 doesn't exist. But this will push us toward, this is where we're ultimately heading, is to try to find mins and maxes on these graphs. And the way we find them is by setting the derivative equal to 0. And then we find the tangent line. If it's 0, means we've reached a max or a min at that spot. All right, so that's two more problems for us.